right. So today we're going to start our next kind of technique of integration, which is all about trig integrals. So they come of the general strategy is there are a lot of trig identities which will be provided for wherever you need them. There will be a formula sheet on the exams. And the point is that we can use those trig identities to set up a U substitution. And depending on which trig functions actually appear, that will influence what substitution you're trying to get to and what does it look like trying to get there. So for example, what if we look at this integral? Integral of sine to the fifth x. One thing with this is, well, a couple of things before we even really get going into how do we handle this. So this is sine x raised to the fifth power. Except for the case, if you ever see a -1 there, that means inverse. So that showed up in the homework. You want to do inverse sine function, not the reciprocal of sine. So this is what we want to integrate. And the thing that makes this sort of a little more advanced is you can't just use the power rule with sine on the inside. Right, and you can't integrate sine and then also use the power rule on the 5 there. Just that isn't what works. If you try that and differentiate, you're not going to get back here. What you would like to do is you look at this and say, well, there's an inside sine function, and that's sort of a U substitution setting. Except if that inside sine is there, you need an outside cosine. So for these powers of trig functions, the U substitution is there is some trig function raised to a power, but you need its derivative somewhere else there. So to make that other stuff show up, that's where the trig identities come in.
If you do 1 plus cosine squared times 1, or 1 minus sine squared of x, and then the sine of x.
So we'll where we end up is kind of big, so we'll see how we get there. And trying to see what the end result is probably from here, making that jump is probably not a good idea because it ends up being kind of big. So here's what we're going to do. The trig identity that will help us is the standard Pythagorean identity sine squared plus cosine squared is 1. This will be given to you whenever you need it, but this on its own is common enough that there's a chance you'll remember it. But this isn't the form that we actually want. What we're going to do is move the cosine to the right side of this equation. Which, if we do that, is sine squared is 1 minus cosine squared. And the reason why this is more helpful is because this says if you have 2 sines, so 2 copies of sine multiplied together, we can replace that with some cosines. And in order to do a U substitution, you need a mix of sines and cosines. So this will help us get that mix. So in order to use this, we need some sine squareds to show up. And that sine to the fifth, we can break apart into 3 different factors. Sine to the fifth is there's 1 sine squared, there's another sine squared, and then there's a single sine left over. Now we have some sine squared showing up, and this trig identity says if you have sine squared, replace it with 1 minus cosine. So first sine squared is 1 minus cosine. Second one is 1 minus cosine. And this sine squared, this just sine on the x, since there's only one copy, we'll leave it as it is. So now as far as just raw stuff in the integral, it looks a lot worse. But having in the back of your mind, we eventually want to get to a u substitution, this is actually a lot better. Because while this part is kind of big, we have this, it's all a bunch of cosines, and we have a single sine off on the side. And this is set up for a u substitution, where all of this cosine stuff can become something in terms of u, and the du is this sine left over at the very end. So now we do the u substitution. Well, there are a couple of ways you can do this. Let me multiply this out now, just for the, because we have to do it sometime. So if you multiply these two 1 minus cosine squareds out, you get cosine to the 4th x minus 2 cosine squared x plus 1, and that whole thing is multiplied by sine x. And like I said, this is a situation where u substitution is going to work. These cosines will get turned into u, and we have the du that we need sitting outside of this integral. Or outside of these parentheses, that leftover sign. So if we want u to be cosine, its derivative is negative sine. There's this minus here we have to deal with. So I'll move that over to the other side. And now we're set up for this substitution. This cosine and this cosine are going to become u's. And then the sine x dx that's left over, that's going to become negative du. Even though cosine appears a bunch of places, every place it appears gets transformed into a u. So what we're left with is there's a negative that I'll stick in front of everything. But then these powers of cosine, like we made this move here, cosine to the 4th now becomes u to the 4th. Cosine squared now becomes u squared. And the one stays at 1. And there's still the tail end of this, but this is the kind of second of this 1-2 punch. We first use the trig identities to change what things look like. And after that change, we're set up to actually do a u substitution, which is the u substitution step is just like u substitutions we've been doing. That's not anything special. What is special is setting ourselves up to do it with these trig identities. So questions about just getting here. We'll finish it to end in a satisfying place, but getting to this point is the hard part. Or yeah, the kind of new thing that we're going to see different ways of doing. So once we're here, then we can crank this out. The negative I'll distribute onto everything. negative u to the fourth plus 2u squared minus 1. This is now it's a polynomial, so everything's a power rule. We get negative u to the fifth over 5 plus 2u cubed over 3. The constant 1 picks up, the variable u. And then u was cosine, so now we stick that in. So we get what's like a polynomial in cosine. Is the way to.
Why are the constant pick up a u instead of an x?
Because the variable is, we're integrating with respect to u, and so that this is saying what the variables are at this point. Yeah. Right, so power sticking cosine in there. 2/3 cosine cubed x minus cosine x plus c, which is the answer that we end with. Questions about this process? More examples will come, and we'll also, after seeing a few instances of this, talk about what is the general situation after seeing what works in some specific cases. So one thing to keep in mind in this is for other problems that maybe have different trig identities we need to use, the step that was really important was getting this part by itself, because we need to get this du. This, whatever it looked like, it was going to become a bunch of u's, and that's fine. But in order to really make the u substitution work, we need to figure out, we need this single trig function to be our du, and everything else is the other trig function. So what if we change this up? We'll leave that there for a second.
Isn't that specific identity called like the double angle formula?
This one is the Pythagorean identity. Double angle is just something else. Yeah, a lot of these are called the Pythagorean identity because they're kind of different versions of sine squared plus cosine squared as well. So what about this? So let's integrate cosine cubed x times sine squared x dx. So now we have our mix of sines and cosines, which means really generally it'll have a lot in common with this. We're going to try to do a u substitution, but we need one thing to be u set aside, and then everything else has to be the other trig function. And when we're looking at this time the du is going to have to be cosine. Because this trig identity that we used here, sine squared is 1 minus cosine squared, that does 2 sines at a time. And if we apply it here, we get rid of all of our sines. And we don't want to get rid of all of them because we need one left over to be a du. So in this case, we don't want to have sine as our du. We look at the cosines and say, this I can separate into the integral of cosine squared x, and then there's the sine squared x, and then there's a single cosine x dx. Rewriting this in a suggestive way that says this single lone cosine, I'm setting that off to the side because that's going to be my du.
Usually it's the thing with like the odd number of powers.
Right. So our trig identity, in this case, the one we're going to use is sine squared is 1 minus cosine. Nope. that's the wrong one. Cosine squared is 1 minus sine squared x. So the reason I wrote that down and said, nope, I'm going on the wrong track is because if we decide this lone cosine is our du, then everything else has to be in terms of sine, which means this cosine that's left, I need to convert that to sine, and that's what this trig identity lets us do. And this thing comes from sine squared is cosine squared, sine squared plus cosine squared is 1, but moved around. That now this lets me turn cosines into sines, just like this move, I was able to turn sines into cosines. So now things are separated. I know ahead of time this is going to be my du. Everything else needs to be in terms of sine, so I can apply this trig identity and get to the integral 1 minus sine squared x sine squared x times cosine x dx. And this is the place that is really well set up for u substitution. I have a bunch of sines and then a single cosine, which will eventually become a bunch of u's, and then the single du that I need to do the u substitution. So questions or clarifications about how we made a different choice of which trig identity we're using because we're heading for a different u substitution. And part of this is knowing what am I looking for that tells me what where I want to get to at the end. So once we're here, and just as something a little bit different, I'm going to do the u substitution now. I'm going to say that u is sine and du is cosine. And now things are set up because this, every place sine squared shows or sine shows up, that becomes a u. So I get the integral of 1 minus u squared times u squared, and then the cosine becomes a du. In the last problem, I did the multiplying first and then the substituting. You can do it in either order. Here, to do this, we still need to multiply this out to get our polynomial. And in this case, it's maybe a little bit easier because there's just powers of u rather than trig functions. So this is negative u to the 4th plus u squared. And then we can run through this pretty quickly. It's a polynomial, so we use the power rule a bunch. Negative u to the 5th over 5 plus u cubed over 3. And u was sine. So we get negative sine to the 5th x over 5 plus sine cubed x over 3 plus b. So in these two cases, the thing that happened was when we looked at our trig function that we started, and this Peter mentioned, one of the powers was odd, and that odd power allowed us to peel one piece off, and then whatever's left is going to be even, and we can apply trig identities to that. But what if we don't have access to that? So what if we just have sine squared of x dx? So given this, we can't just integrate it, but the trig identity, like the two previous examples, would turn this into 1 minus cosine squared. And that's not any better because now you have cosine squared and you can't integrate that. Yeah, so in this case, there's a different trig function. If you're able to peel off this du, then you're able to use the Pythagorean identity to deal with the rest. In this case, and this is one of the trig identities, it just straight replacing it with what it is, sine squared is equal to 1/2 1 minus cosine of 2x dx. So that is a trig identity for getting rid of sine squared. Right, so this one is able to be integrated. There is a 2 inside the cosine, but we are able to move the constants around to find the integral of this. Let's say we distribute the 1/2. And now the 1/2 as a constant, that picks up a variable. And here we haven't done a u substitution, so we can just put x's in. So this first part is 1/2 x. For the second part, the 1/2 stays there, but integrating cosine, cosine becomes sine, but because there's a constant in here, we reverse chain rule this and we divide by that 2 since we're integrating. So we get another 1/2 because of the 2 inside. Cosine becomes sine, then the plus c. And in this step, if you want to be extra careful about where the constant goes, you can do a small u substitution with u equals 2x, and executing that u substitution will tell you where the constant goes. But you always end up dividing by it, so if you remember that, you don't need to actually do the u substitution. Questions about either of these ones?
Get sine to the 4th x, it would be the same thing.
Right, so to start that, and we won't finish it, but if you had the integral of sine to the 4th, then you could write that is sine squared. Well, one way of doing it, yeah, we'll do it this way. You could write that as sine squared squared, and then each of these gets replaced by this one.
So you could have done like, you could have like not simplified the 1/2 1 minus cosine 2x and done u is equal to 1 minus cosine 2x. Oh wait, never mind.
Right, so that, yeah, the 1/2 here has to be brought along, and there's not a slick way of dealing with it other than just you bring it as you're going
How
through.
did you change the 1/4 sine of 2x to the, I mean, how do you change the minus 1/2 cosine 2x to minus 1/4 sine?
So in this case, if you're doing, so this 1/2 is the same one. If you're integrating cosine of 2x dx, then the integral is sine, or cosine integrates to sine, but because you have the 2x in there, it stays in there, but with an extra constant inside your function, any function at all, if you're integrating it, or if that's the only thing extra, so if it's a function you know how to integrate, but there's a constant inside that function, you take that constant and divide by it.
So if it wasn't great, it would be 1/3.
Right. So it doesn't have to be this thing. It could be the integral of e to the 3x dx. You look at this and say e is its own integral, so that I get e to the x back. But because there's a constant in here, I have to divide by that constant. So if the only thing that's different is an extra constant, the end result is you divide by that and integrate the outer function in the way that you know how to do it. So these three examples that we've seen really cover all of the bases, or there are three things that can happen. And while there might be different specific powers, like you could change the 3 and the 2, but there are three situations which are exemplified by the three examples we've seen. So what are the things that can happen? So if you want to evaluate, say, the integral of sine to the m and cosine to the n, which is what we've been doing, different powers of sine and cosine. So example 1 we did is if m is odd, which was example 1 was sine to the 5th. So that was the case that we did there. Then what we did was isolate one of the sine x's. So we took one of the sines and we broke it off from the big power of sine. Use the identity sine squared x is 1 minus cosine squared of x to turn the rest of the sines into cosines. And then the situation is that if you had any cosines to begin with, you left them alone. Then you have the one sine you set off to the side, and then the cosines that you left alone, and the other sines that you converted into more cosines. So then you're able to do u substitution with u is all of the cosines that you have, and du is negative sine x, which is the sine that you set aside from the very beginning. So if you look at that first example, these are the steps that we did. But it would work if you changed that power of sine or if there were cosines to begin with. Step 2, or option 2, is the second example we did, which is basically this same thing, but flipping sines and cosines. So what if n is odd, meaning you had an odd number of cosines? In the example we did, we had 3 cosines, so that's why we were in this case. Then it reads really similarly. You have an odd number of cosines, so isolate one of those cosines. Use cosine squared x is 1 minus sine squared x. To turn the other cosines into sines. And then you can do substitution with. Now you have a bunch of sines and this single cosine that's left on the side. So u is sine. So all of those sines will become u. And then this single cosine you left off to the side is your du. Little star is if both powers are odd, then either of one or two works. So if it was sine cubed, cosine cubed, then you're in either one of these cases. So whichever one you go for will end up working. And then 3 is this situation, or the remaining case, which isn't covered here, is if both powers are even, use their half, or I don't know which one it is. They're either the half or double angle identities. Which you would be given, but it's more know that this is the annoying case, but in this annoying case, there are identities that are specifically useful in this case. And to give an idea, let me actually do this one, because the general outline is really similar to this, but it's when that power gets bigger, a little happens that's maybe unexpected. And so I don't know if I'll finish it all the way, but we'll see what it looks like when that power actually gets bigger. So if we have the integral of sine to the 4th x, like I said, that was sine squared times sine squared. And then like the thing I just erased, sine squared, we don't want to turn it into cosine squared because then we're still in case 3 with all these even powers. We want to use these other identities. So the one that we used when we just had sine squared was that 1 minus, or sine squared is 1/2 1 minus cosine 2x. And then we have another sine squared. So that is 1 minus cosine 2x. Which is good. We don't have powers anymore, but then we multiply this out. I'll put the 1/2 and 1/2, that's a 4th. I'll stick that outside for now. But then on the inside, we get something which we're not excited to see. Cosine of 2x, or negative cosine 2x times negative cosine 2x is cosine squared of 2x. The cross term is negative 2 cosine 2x, and then the 1 times the 1. So we multiply this out, and what happens and why I call this the annoying case is if that power is bigger, we have another cosine squared, which is actually back in this case. We had gotten rid of the powers, but another power shows up. So when you get down to integrating this thing, you need to circle back and say, I have an even power of cosine. I deal with that by using this half angle identity. Cosine, we haven't used that one today yet. So the identity is cosine squared of, I'm going to change this variable to be y is 1/2 1 plus cosine of 2y. And in this case, the way we need to think of this is this identity applies no matter what y is. Whatever it is, you're going to have all of this stuff and 2 times whatever was initially inside your trig function. So that means we have a 2x, that's fine. When we the 2x, because it's inside there. No, so it is squared, but there's also a 2x on the inside. So it's squared because we multiplied it times itself. The 2 comes because that's the trig identity. Sine squared of something is 1/2 1 minus cosine of 2 times that thing. So the 2 shows up as part of the trig identity. But then how we deal with this case is we use this formula. It is 1/2 1 plus cosine. But the thing inside cosine is 2 times what we started with. Which, since we started with 2x, now we get a 4x. And so that's a small thing that we need to keep track of, but is something that happens if you have higher even powers. But, and I'll stop here because we're in a doable place for this integral, because even with the 4, we integrate that basically in the same way we integrated this cosine of 2x. There aren't any powers, there are constants inside the trig function, but that's doable. So with these higher even powers, we sometimes have to use these trig identities more than once. And I'll say, if this power gets really big, you have to do a lot of these, which is why we won't ever see powers be very big. Having just even powers, they won't ever be bigger than sine to the 4th because, or sine or cosine to the 4th, just because there's not much learning of new stuff that goes beyond those powers. But there is this kind of different thing that happens, and I wanted to at least show that. So this was all sines and cosine, which is good. But that's not the only pair of trig functions that we can use this strategy with. So there's a similar strategy for the integral with tangents and secants. So tangent to the mx, secant to the nx. So if instead of sines and cosines, you have tangents and secants, there's this similar combination of there are some trig identities that let you move between the two of them. And then there are u substitutions that are useful if you have the right combinations of these. So those identities there are two versions of it. There is tangent squared is secant squared minus 1, or moving the 1 to the other side, we get secant is tangent squared plus 1. So these are the identities that let you take tangents and turn them into secants, or secants that turn them into tangents. So that's one of the things we need to switch between the ones that we have. And then there are two versions of u subs which aren't perfectly symmetric. So with sines and cosines, they looked basically the same. With tangent and secant, it's a different combination. So you can either have u is tangent, and then du is secant squared, or if u is secant, the derivative of secant is secant tangent. So by similar strategy, I mean, and I'll lay this out in kind of more detail after a couple examples, but the similar strategy means given your bunch of tangents and secants, you want to isolate one of the du's and have everything else in terms of the corresponding u. And how you get just that bunch of u's is using the correct trig identity to switch what you have into entirely the trig function that you want. And because the du's are, they're just different looking, it's a little bit different than the sines and cosines, where it all came down to, do you have an odd number or an even number? So what about this? The integral of tangent squared secant to the fourth. So in this case, we have both of these things in here. We have two secants, and we have at least one of each kind of secant is tangent. So we need to think about, for each of these possible du's, if we set that aside, so if we set aside secant tangent, can we turn everything else into secants? And if we set aside a secant, can we turn everything else into tangent? That's the decision that needs to get made about which u substitution we're going to try to go for. So using red for this doesn't work. If you set aside a secant and a tangent, then you have one tangent left, three secants left, and then your secant x tangent x. So if that's what you decide to do, you're kind of stuck because you need everything else to be just secants in order to get this u substitution to work, and it's not going to happen. This one tangent, you're kind of stuck with. And so we'll go the other way. So skip over that. That is when I say that is it is true that these are equal, but it's not really useful. So instead, we say we have the tangent squared and then secant squared, and then another secant squared, where this thing off to the right, we're saying that's going to be our du. Can I turn everything else into now tangent? And in this case, this is going to work because we're left with a single secant squared, and we're able to turn that into just tangents. So we are able to set this up as a bunch of tangents and then a secant squared off to the side, and that paves the way for our u substitution. So the tangent squared that's already there is left alone. Secant becomes tangent squared x plus 1. And then our du that we set aside is there. And now we're ready to u substitute. Before we actually do that, kind of questions, concerns, clarifications about getting to this point. This is, I think, it is important to see more of these so you get used to what kind of, or how do I move these around in different arrangements. But keeping in mind that what u substitutions there are at the end is important because that's what you're able to do. So then we can actually execute this. U is tangent. Du is secant squared. It's all nice and set up and separated. In this case, we don't even have any constants to deal with, or a negative sign to move around. So we get u squared plus 1 du, another polynomial after we multiply it out. U to the 4th plus u squared, power rule, u to the 5th over 5 plus u cubed over 3. And then u was tangent, so we stick that in there. Tangent to the 5th x over 5 plus tangent cubed x over 3. What's about this one?
Why is it that tangent and secant are related instead of like cotangent or like secant and cosine?
So it's really, I mean, kind of a really deep reason. I'm not really sure. Practically, it's because both there are identities connecting them, and they are, when you take derivatives, they both kind of appear in each other's derivatives. So there's also this third pair, cotangent and cosecant. They also appear in identities with each other and appear as each other's derivatives. So it just is really why I don't have a great explanation, but there seem to be these 3 clusters of pairs of functions that appear in the combinations that need to appear in order for this to work. Okay. So on Monday, we'll keep talking about this and seeing other ways of integrating trig functions, but along these kind of same lines. All right. So I'll see everyone next week.